Hi everybody, welcome to your Test 2 review. So this is for spring 2023. So in general, the format's going to be super similar to the last test, and as always you can bring a 3-inch by 5-inch index card with equations on it for you. I'm going to give you the constants sheet, so no need to write constants on your note card. Those will be provided. And if you need the differential forms in the inside back cover of your textbook, those will be provided too. This test is going to cover from Purcell and Moore in Chapter 3, 4, and some of Chapter 6, and also a little bit of Chapter 10 on dielectrics. So if you need some review, of course your matter and interactions text is a little bit more friendly, but it's in kind of a strange order. So what I'm going to do here is just provide you a list of the topics, and then you can look up in matter and interactions where those are covered if you'd like the sort of more like a 1000 level physics review. Okay, so Chapter 3, we started talking about capacitors. Capacitors are charge and energy storage devices. The equation for a capacitor is that the capacitance C is equal to the charge stored on the capacitor, which is Q, divided by the voltage in between the plates, V. So the SI unit for capacitor is the farad, which is a coulomb per volt. It's a very large unit. Most capacitors are micro, pico, nanofarad ranges. And remember that the capacitance of a capacitor depends only on the geometry of the object and whether or not there's dielectric there. It's really worthwhile to remember and maybe write on your note card the equation for the parallel plate capacitor. C is equal to epsilon naught A over D. Remember that epsilon naught is that fundamental constant in the permittivity of free space. That's 8.854 times 10 to the minus 12 in SI units. A is the area of one of the capacitor plates, and D is the distance in between the plates. So you can see from that just given this simple example, that the capacitance for any capacitor would be, geometrically dependent, as is this equation for a parallel plate. The energy stored on a capacitor is given by U. Potential energy storage is equal to 1/2 Q times delta V. So here 1/2 times the charge stored on the plates times the voltage. And then you can use the C is equal to Q over delta V equation to get it into different forms. When you use capacitors in circuits, we often speak of the equivalent capacitance if you have multiple capacitors hooked up in either series or parallel. So if you have a bunch of capacitors that are in parallel to one another, then to find the equivalent capacitance, you just add them up. And if they're in series, then to find the equivalent capacitance, you take 1 over C1 plus 1 over C2, and then that gives you 1 over the equivalent capacitance for the capacitors in series. Remember that we had some problems in homework and in class where we solved for, if you had multiple capacitors hooked up to a battery, for example, what the voltage was and what the charge stored was and what the energy stored in each one of the capacitors hooked up to the battery is. So to do that, remember that if you have a whole bunch of capacitors in series to one another, then the charge stored on those capacitors in series will be the same. And remember that the voltage drop over capacitors that are in parallel is going to be the same. And the voltage drop for capacitors in series adds. Okay. Also remember that, as is the case for any circuit, the total voltage drop over all the circuit components has to equal the voltage that the battery is supplying. The battery is the source of that voltage, so it makes sense that all the drops have to equal the voltage that the battery is supplying. Okay, dielectrics are insulating materials that are placed in between capacitor plates. And the dielectric serves to provide physical support for the capacitor so that the plates don't short out, but it also has the nice side effect of increasing the charge stored and the capacitance of your capacitor. We quantify how much the capacitance increases by something called the dielectric constant, which is a dimensionless number that's greater than 1 generally. And it's usually abbreviated by the Greek letter kappa, okay? And it's equal to the permittivity of the material, epsilon, divided by the permittivity of a vacuum, epsilon naught, the fundamental constant. Now, dielectrics increase the capacitance of the capacitor proportionately. So whatever the capacitance is without the dielectric, I'll call that C naught. Then the capacitance with the dielectric is equal to kappa times C naught. Okay, now when you increase the capacitance in the capacitor plates, you're actually reducing the total electric field between those plates by the dielectric constant. So the electric field between the plates of a capacitor that has a dielectric is going to equal to what the electric field would be without that dielectric, E naught, divided by kappa. Also remember, we defined something called the dielectric strength of the material. We had a homework question on that. And the dielectric strength of the material is the max electric field the material can withstand before breakdown, okay? It's a material property. So basically, if you ramp up the voltage too high, you'll get a spark in between your capacitor plates and your capacitor will discharge. And that's what we mean when we say, breakdown. Remember that you can always relate the voltage to the field, this is generally true, with the equation delta V is equal to the negative integral of E dot ds. And so, for example, for a parallel plate capacitor, the voltage in between the capacitor plates will be equal to the electric field in between the plates times the distance in between the capacitor plates. Dielectrics work by storing charge on the surfaces of the material. Charge also is stored on the capacitor's metal plates, which is how it increases the total amount of charge stored when you put a dielectric in. This charge that's stored on the capacitor is called the bound charge, and the density of the bound charge on the surface of the dielectric is related to the density of the charge on the surface of the capacitor, via the formula sigma induced is equal to sigma naught times 1 minus 1 over kappa. We talked about the polarizability in an online lecture. That was one of those flip days when I wasn't there. And how easy it is to polarize this material is summed up by a quantity called the polarizability, which is a vector P. The polarizability is the average dipole moment per unit volume that you get in the presence of an electric field. It can be written P is equal to epsilon naught E times kappa minus 1. So you can see that it depends upon the material properties because it's dependent upon kappa, which depends on the material. Kappa changes for different materials. So to summarize, here's a little schematic and what the schematics are saying in words. When you have an externally applied electric field in an insulating material, that material becomes polarized, as is shown in the little cartoon with the plus and minus charges. Dipole moments are induced, and then they rotate to align with that external field, and that creates a net dipole moment per unit volume in the material. The polarization of the material causes an electric field in the material that's opposite to the externally applied field, and that reduces the net field in the material by the dielectric constant. And you can see here the picture of the induced charge on the surface of the capacitor and the bound charge on the capacitor plates. Okay, chapter 4. Here's where we started talking about the model of current and how charge flows in conductors. So first we defined current. The current is the charge that passes some, threshold point or some standard point per unit time. The average current is delta Q over delta T, the amount of charge that passes the threshold point in an amount of time delta T. But you can also take the derivative of that, and the instantaneous current or regular current is I is equal to dQ dt. So you measure that current, like I said, by counting the number of charge carriers that pass the reference point and then multiplying that by the charge of each carrier and then dividing by the time interval. We used the semi-classical model of conduction in this class. It's called the Drude model of conduction. Now in this model, the charge carriers are pictured as moving these crazy little zigzaggy paths. And this is because they feel a force due to some applied voltage, which creates that electric field, F equals QE. So they accelerate under the influence of the field, but they keep running into obstacles, defects in the material, other electrons, things like that. And that causes them to bounce off those obstacles into a new velocity direction, as is shown in this little sketch up here, okay? But because they're experiencing that net force in the direction, they are going to have a slow drift velocity, okay? Now remember that in a conductor, the charge carriers are electrons, and those electrons want to move upstream on the electric field, which is why in the little sketch up here, your electric field is to the left, but your drift velocity is to the right, because the charge carriers here are electrons, okay? So you always have these free electrons in a metal, and they're always zigzagging and running around at really high speeds in between their collisions. The Fermi speed of electrons in materials is, 10 to the 6th meters per second or so, but they have a lot of collisions, and so the drift speeds are low. Even in the absence of an electric field, the electrons are moving around. It's just that there's no net motion unless there's an applied field. So here's a little Drude conduction model that we discussed in class. We derived the fact that the current in the Drude model of conduction, I, is equal to NQA times V sub D. Here, N is the charge carrier density, which is the number of charge carriers per unit volume. Q is the charge on a single charge carrier. A is the cross-sectional area of the wire, or whatever medium you're in. And V sub D is what we call the drift velocity, which is the net average velocity of the charge carriers. So usually, like I said in metals, this drift velocity is decently low, even though they're experiencing a large acceleration from the field because of all the collisions the electrons have. Make sure that you can solve this equation and apply it. Solve for N from a material density and all that good stuff. These are all questions that got covered in homework and in class. We also defined the current density. The current density is the amount of current per unit cross-sectional area of your wire. So however much current is flowing in the wire, you take that and divide that by the cross-sectional area of your wire, and you have the magnitude of the current density. Now, in one form of Ohm's law, the current density is written as being proportional to the electric field. The constant of proportionality, is J is equal to sigma E. Sigma is the conductivity. The conductivity is a material property that changes from material to material. Some materials, of course, are more conductive than others. Remember also that the conductivity is equal to 1 over the resistivity, which is, very confusingly, often written as rho. I know that we use rho for density too, and I'm sorry for that, but we're just stuck, okay? So sigma, the conductivity, 1 over the resistivity, is equal to NQ squared tau over M, okay? N again is the charge carrier density. Q again is the charge on the charge carrier. Tau is called the mean free time between collisions, which is defined as the average amount of time between each collision that the charge carriers have, and M is the mass of the charge carrier. We talked about the equation for resistance and how it was related to resistivity. If you have a conductor of length L and cross-sectional area A, then the resistance of that conductor is going to be equal to rho L over A, where rho is the resistivity. And then from this expression, and J is equal to sigma E, we can derive the second form of Ohm's law, which is V is equal to IR. This is the one that you're probably familiar with from an intro physics class. Here, V, the voltage, is equal to the current times the resistance of your resistor or circuit element. So, we reviewed the types of materials, which are conductors, insulators, and semiconductors. Conductors are metals, and they have free charge carriers. Semiconductors have valence electrons that can be promoted to conduction electrons without much energy. And so it happens a lot with heat or an decently low applied voltage. And with insulators, of course, you can still create free charge carriers, but it takes about 10 times more energy. So you can get anything to spark, for example, if you apply a high enough voltage, but sometimes it takes a lot of voltage. In electrical circuits, the rate at which work is done, or the power, can be described via the equation P is equal to IV, which is equal to V squared over R, which is equal to I squared R. And this is taking P is equal to IV and then using the second form of Ohm's law, V is equal to IR, to get the other forms. If you have a bunch of resistors and you want to find the equivalent resistance, then you add up the resistance to find the equivalent resistance if the resistors are in series. And if they're in parallel, then the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistors. In other words, 1 over R equivalent is equal to 1 over R1 plus 1 over R2 for 2 resistors. Of course, it keeps going if you've got more than 2. Be sure that you can, given a circuit with a battery and a bunch of resistors in it, find the equivalent resistance for the circuit, and also be sure that you can find the power dissipated in a resistor and the voltage drop across resistors in individual problems. So in order to do this, what we did was we realized that the current through resistors in series is the same, and that the voltage drop across resistors in parallel is the same. So that's a key idea that we used in those types of problems. Okay, next, Kirchhoff's rules. If you have a circuit with multiple batteries or circuit components of different types, okay, then you might need to use Kirchhoff's rules instead of just finding the equivalent resistance or the equivalent capacitance and going, okay? So for more complex circuits, Kirchhoff's rules are your friends. There's two of them. There's the loop rule and the junction rule. Junction rule says that the current that flows into a junction has to equal the current that flows out of the junction. This implies that there's not a junction as well, by the way. It's just really a restatement of the conservation of charge. You can't create or destroy charge, so if it goes in, it has to come out. Kirchhoff's loop rule states that if you make a complete closed loop in any circuit, then the sum of the voltage changes across all the components has to be zero. This is really just a restatement of conservation of energy. If you make a closed loop, you got to end up back where you started. So make sure that you can use these and apply them in circuits. Okay, next we talk about RC circuits, which are capacitors that have a resistor, circuits that have a resistor and a capacitor in them, and also maybe batteries and switches, of course. So if you've got a capacitor and a resistor hooked up to a battery, then you have a charging RC circuit. That means that the capacitor is gaining charge as time goes on. Of course, once the capacitor is all charged up, no more current will flow through that branch of the circuit or capacitor, okay? So it's going to increase exponentially with time. The charge on a capacitor with time will equal to the max possible charge, which is, by the way, dictated by the equation C is equal to Q over delta V. So the max possible charge times 1 minus e to the minus t over RC. Okay? Here, RC is the time constant, okay? And it does have units of time, however strange that might seem. You're just multiplying the resistance times the capacitance of the circuit. Now, if you have a charged capacitor and a resistor in series but no battery, then what will happen is that the capacitor will act as the power source for the circuit, and it will cause current to flow. So that's a discharging capacitor circuit, and in that case, the charge on the capacitor will decrease exponentially with time. So the equation for that is Q of t will be equal to the max charge on the capacitor when it starts flowing, right, times e to the minus t over RC. So you see that exponential decay. Now, for either one of these equations for capacitance, the charge on a capacitor, the charging or the discharging, remember that the current is related to the charge via dq dt. So if I take the derivative of either one of these equations, then I have the equation for how the current is going to flow in that RC circuit. So for a charging RC circuit, the current is going to decay exponentially. In other words, as the charge builds up on the plates of the capacitor, the current will get lower and lower until it completely stops when the capacitor is charged. So the equation for that, I of t, is equal to the max current, which is going to be the EMF of the battery divided by the total resistance of the circuit, EMF over R, times e to the minus t over RC. For a discharging capacitor, the current equation is I of t is equal to minus Q max over RC times e to the minus t over RC. So in that case, the current is going to exponentially decay as the charge bleeds off of the capacitor and it has less oomph to supply the circuit. The minus sign there just indicates that the current is flowing away from the positive plate when the capacitor is discharging, whereas of course the current is flowing towards the positive plate when the capacitor is charging up. Okay, Chapter 6. We didn't get too far into Chapter 6 for this test, but we did define the magnetic field and talk about the sources and the values of the magnetic field. Okay, so first things first, the SI unit of the magnetic field is called the Tesla. The Tesla is actually a really big unit. The MRIs have about 10 Tesla. 2 Tesla can pick up a car, and the Earth's magnetic field is 25 to 65 microtesla, depending on where you are. Since the Tesla is such a large unit, oftentimes we'll use the Gauss instead of the Tesla. So 10 to the 4th Gauss is 1 Tesla. Magnetic fields are caused by currents, okay, moving charges, and changing electric fields and magnetic materials. But even for the magnetic materials one, at the root, that's still currents and moving charges, okay? So we had a couple of equations for finding the magnetic field created by different sources. So first of all, if you just have one moving charge, then the magnetic field for that moving charge is given by the BOSR law, which is equal to mu naught over 4 pi times QV cross R hat over R squared. Okay. Here mu naught is the permeability of free space, a fundamental constant of nature, 4 pi times 10 to the minus 7 in SI units. And then Q is the charge, V is the velocity of the particle, R is the distance between the charge and the point where you want to know the magnetic field, which I call the point in question, and R hat is the unit vector that points from the charge to the point. So this QV cross R hat is a vector cross product, so the direction of the magnetic field at this point is given by the right-hand rule, which you should definitely practice. If you have a bunch of moving charges, then you have a current, and this gives you another form of the Biot-Savart law. So dB here, just the little differential portion of the magnetic field, is equal to mu naught over 4 pi times I ds cross R hat over R squared. And then to get the total magnetic field, you just integrate over the whole current distribution by integrating over ds. So make sure that you understand that this is the magnetic field due to the current carrying conductor. Don't confuse this with any field that might be external to that conductor. Remember here that current is defined as the direction of positive charge flow. So if it's the motion of an electron or some kind of negative charge, then that's going to flip the sign, okay? And that you're going to have to integrate dB to get the total magnetic field. The Biot-Savart law is good for situations where you don't have a nice symmetry, okay? So finite lengths of wire, arcs of circles, things like that. We covered Gauss's law for magnetism. Basically, Gauss's law for magnetism says that you don't have any magnetic monopoles. In other words, all magnetic fields come in pairs, a north and a south pole, right? And so if you tried to place a Gaussian surface around a magnet, then what goes in comes out in terms of the magnetic field. You can see here that when I place a surface around my north-south pole of my magnet, I've got field lines pointing out from the north pole and coming into the south pole. So what's leaving that oval comes back in on the other side. So there's no net flux. And the same could be said for any circle or closed surface that I drew here. What goes in comes out. So basically that's Gauss's law for magnetism, that if you integrate about the enclosed surface of B dot dA, that you'll get 0 because there's no magnetic monopoles. And then we went through a derivation to show that the differential form of Gauss's law for magnetism is del dot B is equal to 0. Okay, Ampere's law is the other way that you can find what the magnetic field is due to a current distribution. It says that if you take the line integral of the magnetic field about a closed loop, then it's going to be proportional to the current enclosed by that loop. So, written out in integral form, the integral of B dot ds about the closed surface is equal to mu naught, that fundamental constant, times the enclosed current, I sub E and C. Now this could also be written as mu naught integral of J dot dA, okay? Remember that J is the current density, which is I over A. So if you integrate the current density over the area enclosed by the loop, you're going to get the enclosed current times that mu naught gives you the integral of B dot ds. In differential form, Ampere's law is written as del cross B is equal to mu naught J. So what you do with this, especially the integral form, is you can solve for what the magnitude of the magnetic field is due to symmetric current distributions, like really long wires, solenoids, toroids, things like that, okay? So you should, I think, just go ahead and make sure that you're super familiar with the magnetic fields for long straight wires, both inside and outside, okay? Current loops in the center of the loop, solenoids, which is a cylinder with a wire wrapped around it, and toroids, which is a donut solenoid. Okay, make sure that you know how to do those. All right, we're going to leave off there. The Lorentz force law and things like that is going to be covered on the next test because you haven't had any homework on it. And so that's what's going to be covered on this test. Happy studying, and I'll see you in class tomorrow.